All right, so we're going to be today making an open top box out of a piece of cardboard. It's 14 by 32 inches. And to do this, what we're going to do is we're going to cut corners out of the edge, square corners out of the edge, and then fold up the little wing tabs on the side and tape it up. And I always picture like we're maybe making like a cake box or something, like a sheet cake box, if you can figure or look at that. So here's the flat version of it. I start out with this piece of cardboard. Look how squiggly my things are. I'm not shaky. It's not like I had too much coffee or anything. I don't know why it's all wiggly like that. And then we take a scissors and we cut out these little corners. And I just cut out squares on the corners. And then what that leaves me left with are these little tabs. Can you visualize what I'm saying here? And then I just fold those tabs up and tape it. I can even show you like a very rough. So here's my flat piece of cardboard. I cut out squares. I'm not doing a great job of making them the same size squares, but it's pressure. You guys are watching me. I get nervous. Okay, so there I have my flat piece. Good. This is my cardboard. I cut my squares out, and then I just fold them up. Tape them up, and I create a box-ish sort of thing. Okay? So that's what we've got going on here. So now we get to practice our skills at drawing three-dimensional figures. This is where things get a little rough. Please know this. I will never, ever, ever judge you for your drawings. Okay? So just try to make it. If it doesn't work for you and you need me to draw it for you on your paper, I would gladly do that. Okay? So to make my box, what I do is I start with a parallelogram. You know what a parallelogram is? It's a rectangle that's sort of tipped to the side. I make it kind of a flat parallelogram because I want to try and give the illusion of dimension here. And then I make the sides of my parallelogram on the outside what are showing. So I just put same length sides down, and again I want to give some sort of perspective. So I put one sort of shorter in the back, get the feel of it. And then I will continue to connect the box pieces. Because this is an open face box, I will have like an inside here that I can also see. Not important detail to draw, but there is my open face. Again, I picture like a cake box kind of thing. Sheet pancake. All right, now here's the thing. I want this to hold the biggest amount of cake possible. I want it to be the largest possible volume. And I started with a 14 by 32 inch piece of cardboard. And I cut out a certain size of square. And a square has both the sides the same. And so I have like an X by X square cut out of each corner. So what that does is, when I look at my new dimensions for that side, if I'm going to cut out X and X, I have a length that is 14 less the 2X lengths that I cut out. Good? And then same with this one, 32. The full length was 32, but I cut out this X, I cut out this X, so I have a 32 less the 2X lengths I cut out of that length of this. And then, because the square was X in dimension, that makes my height a height of X. And all the problems that we do like this, where we have a supermarket employee doing this, they're all pretty much the same, okay? I want the largest possible volume. Who remembers how you find volume? Beautiful. So my volume function is my length, actually, I'm going to do it not in order. I always like to put the x first. So I'm going to call the x my height, actually. And then my length is, and width, and all get multiplied together. So again, not necessarily in the right order. I just like to put the single x first. And then I need to multiply this through so that I can clean it up. And then I'll go ahead and I'll take my derivative. Now I could do this. I could multiply the x through that first thing, and then the 32 minus 2x is there. And I could do the product rule when I do my derivative. First d second plus second d first. Courtney said, but who would do that? Or I can distribute this all through and come up with a polynomial function, and that's usually the preference. The only problem is when people do the multiply all through, it feels like you do a lot of work and then you're done and then you forget to take your derivative and finish it off, whatever. But, so just watch out for that. Okay, so I have to do the multiplying here. I'm going to do 14 times 32, and I get 448x minus 28x squared minus 64x squared plus 4x cubed. So that wasn't too painful. Jonathan's got the people's eyebrow going on. You okay?
Yep.
Okay. Then I'm going to, again, clean this up a little bit. I like to get my 4x cubed in the front. I'll combine these terms, so that's minus 8092x squared, and then plus 448x. And once I have my cleanup done, then I can take my derivative. All of these problems are optimization problems, and so all of them are going to require a derivative. And you can do the derivative early on before you simplify, or later on after you simplify, and it doesn't matter either way. But here I am. My derivative is 12x squared minus 184x plus 448. And I'm going to set this equal to 0. And I'm going to go ahead and solve for x. It's a squared. That makes it a quadratic function. That means it's a parabola. That means I can do two things to solve this. I can either factor to solve. These numbers are way too big for me to want to do that. I'm going to end up doing 12 times 448, or I'll see if I can take something out, but the numbers are going to be big. And I'm not even guaranteed that it factors nicely. So my option number 2 is quadratic formula. I should say you could also complete the square, but I don't recommend that with a problem like this anyways. So I would do quadratic formula. A is 12, B is negative 184, and C is 448. Quadratic formula, again, is always up here. I know that's not super easy to see for you guys all over the place, so when you take your test, I will have it on a little note sheet for you. So this is the opposite of B plus or minus the square root of B squared minus 4 times A times C. It's really jammed in there. All over 2 times A. I'm actually going to figure out, yeah, I can do it this way. I need a better calculator than the little one I'm using. So it is parenthesis 1, negative 184 squared. I really don't even need the negative because it's going to square and come positive. So even though it's negative in that formula, when you square it, it becomes positive. So you can just drop it if you want to. Minus 4 times 12 times 448. I got 123.52, so 12,352 all over 24. And now I can set up my two equations that I'm going to use to solve this. It's 184 plus the square root of that over 24, and it's 184 minus the square root of that all over 24. Make sure you hit equals before you divide. And I got 12, my x to be roughly 12.3. Does anybody agree with me? Okay, great. And then I'll do the next one, 184 minus, hit equals, and divide by 24. And my next one is roughly 3.04. I don't want to round all the way to 3 because I know it's not exactly 3. So I will do 3.04, give me a little bit. This is the first time that when we've been done, we've actually had 2 different answers. And so I really I need to figure out which one of these answers is going to be the one that works for me or the most reasonable. And that's where this F prime chart comes into play. I could put 3.04 on here, and I can put 12.3 on here, but my math isn't going to be super duper easy when I do that. So I want to try and pick really easy numbers. I'll use 1. So that's going to be 12 minus 184. That's negative 100 something. Plus a positive 400 something, so this is going to be a positive region, so I'm increasing there. Then I'm going to try something like, I'm going to use 10, because 10 is an easy number for me to work with. So this is going to be 12 times 10 squared, so that's 1200. So 1200 minus 1,840, because it's 184 times 10. That's going to be like negative 600 something-ish. And then plus the 448, that keeps me in a negative region, so I know that's negative. So I'm decreasing. And then, again, I'll try something sort of easy. And sometimes I do a cheat and I just plug it in my calculator just because it's much easier to do that. Regardless of the method that you do, this part does come out positive. So that makes 12.3 a min and 3.04 a max. And I wanted the largest possible, so I am going to cut out 3.04 inch squares. Another thing that you can kind of keep in mind is common sense. And if you look at the 2 values that you got and think about what's happening, if I were to cut out 12.3 inch squares from each corner, that means that the 2x would already be like 24, more than 24. Well, can I cut 24 inches from a 14-inch side? No. So that's another thing that you can use to eliminate. So when you're going through problems, you can kind of think of stuff like that. But that is sample type problem number 4, I think, right now. Please give number 9 a try. See if you can do that same type of problem. You can follow through the same thing. It follows the same process. Only thing that changes are the numbers. Okay, how many people actually were able to get the 2-inch squares? Did it work out for us okay? Good, good. Again, I know it's very mathy. This is very mathy, and sometimes the words are scary, but don't be afraid. Here's our next type. This is a graphic designer being asked to do a poster, and the requirements for the poster is that it has to be 50 inches squared, But then it has to be, like, the photo itself is 50 inches squared, and then they require a border around it so it's aesthetically pleasing or whatever the case may be. And so our job, after we incorporate the 2-inch border on the top and on the bottom and the 1-inch border on each side, we want to find the overall dimensions of the poster so that they use the least amount of paper. We're just trying to be efficient and economical, okay? So I'm going to do the drawing. Here is the photo that goes on the poster. And this has dimensions of x times y, and I know that x times y has to be 50 inches squared. That's the requirement for the photo. But then, on top of that, I have to make sure I have enough paper to put a border around that picture, and again, it's all about aesthetics. I want it to look pretty. Because I can't jam the picture right up to the edge of the paper. I need something to frame it. And they said that I have a 2-inch border at the top, so this length right here is 2 inches. And I have a 2-inch border at the bottom. This length right here at the bottom is also 2 inches. And then on the sides, I have a 1-inch border, so I have a 1 inch on the left, and I have a 1 inch on the right. So I need to figure out my new height and my new length along the bottom. So my height here is this whole measure, and it's the 2 plus the y plus the 2. So the top part, 2 inches, plus the y length, plus another 2 inches, and so I'll call that y plus 4. Is everybody all right with that? Seem reasonable? And then I'm going to do the same thing along the side here. I'm looking for this new width or length, and that's the 1-inch border plus the x length plus another 1-inch border, so I'll call that x plus 2. And I want to minimize the amount of paper used, and the amount of paper used is going to be the new area, including the border. So my paper use, I'll just call that P. You can name any function, call your function anything you want. I'm going to do paper used is P, and that is x plus 2 times y plus 4, length times width. That's the area of the paper that I'm going to be using to make this poster. All right, I run into a problem. Because at this stage in our career in derivatives, which is what I have to do next, I cannot take a derivative on 2 different variables. When you get into calculus, you will be able to do that. But at this point, we need to have it down to just one variable in my function. So I either need to solve for x and solve for y so that I can get it in terms of one variable. Usually, generally speaking, I solve for y, but there is no rule that that's how it has to be. So if you're like a person that likes to solve for x more, great, then your equation is just going to have y in it that you take your derivative on. So the whole point of doing this is so that I can replace my y with something in terms of x, and I can create a new equation that has now only one variable. Some people don't like that x in the denominator, and all I can say is get over it. We can deal with it. It's not bad. So I'm going to distribute and solve. So x times 50 over x is going to give me just 50 because the x's are going to cancel each other out. And then x times 4 is plus 4x, not 40, plus 4x. And then the 2 times 50 over x will give me 100 over x. And then the 2 times the 4 gives me 8. So my now function for the paper is 58 plus 4x plus 100 over x. And the 100 over x is a nice way if I'm trying to solve or evaluate. But 100 over x is not a nice way to write that term if I want to do a derivative. Because I would have to do a quotient rule mixed in with this power rule as I go through here. So what I'm going to do instead is, to help make my life a little bit easier, I'm just going to write that as 100 times x to the negative first power. Because that's an easy power to work with to do a derivative. Are we okay with that? Everybody all right with that? Anybody have a problem? Otherwise, I'd have to do a low d high minus high d low over low low, and again, it's doable, but I don't want to. Now I'll do my derivative. The constant's going to zero out, so that's 4 minus 100 x to the negative second power. Now I have to set it equal to 0 and solve. And because I'm solving, the negative power is not good. Negative power is easy to take a derivative on. Negative power is not easy to solve with. So I am going to rewrite this as 4 minus 100 over x squared. So I'm just sort of bouncing that negative power around a little bit and using it when it's easy to work with, but taking it out of there when it's not. So now I have to solve for this. I'm going to add the 100 over x squared onto the left. I'll multiply the x squared out. So that it's not in the denominator anymore. Basically, I'm just multiplying both sides by x squared. We've done this before. I'll divide by 4. And I'll take the square root. Here's another time where, yes, when I take the square root of 25, I get plus or minus 5. But when I think about it, is negative 5 even an option for a measure? No, not when we're talking about length here. So my x is going to be restricted to just 5. And I'll just double check and make sure 5 is what I want it to be. And I'll plug it into this guy here. If I do 1, it is 4 minus 100 divided by 1, and that is definitely a negative region. And if I do something like 10, it is 4 minus 100 divided by 100, which would be a positive region. And yes, that is in fact a min. Okay? Now, be careful, because this says what overall dimensions for the poster should be used. X is the length of the picture. Okay? So I got X to be 5. And Y is 50 divided by 5, or 10. Good. But the actual height is Y plus 4. So it is 14 inches by, and then I go back with my X, the actual width of the poster is X plus 2, so it's 14 inches by 7 inches for my final dimension. So a little added step that you have to do on this one. Again, I'm going to pause this, and I'm going to let you try number 11. Similar setup, just kind of have to change around the actual numbers. Again, on this, how many of you were able to get 26 by 13? Pretty good. Really, for the most part, it's just a matter of getting comfortable with the wording and changing up, making sure you're safe on your math. But our last one is another three-dimensional figure. This one is making a box-shaped aquarium with a square bottom. And we have a requirement for this aquarium. It has to hold 256 feet cubed of water. And detail is important. Attention to detail is important. Cubic measurements are volume. Square measurements are area. Single measurements, just a foot or an inch, is like a linear measurement. And so this cubed tells me I'm looking at 3 dimensions. And so my connector is going to be a 3-dimensional combination of lengths. We have to figure out what the dimensions are that would create this acceptable aquarium, but I want to use the least amount of glass. So I'm trying to, again, conserve the amount of product that I'm using, but still make it come up to the right dimensions or cover what's necessary. And so I will start by drawing my aquarium. It has a square base, so I'm making, again, a parallelogram to start with, just like we did our other one. And from that parallelogram, again, I'm giving it some sort of like perspective. I need to have some height in my tank that I'm using so the fish have room to swim. And then I want to make sure that I incorporate the base of this. Now they did say that this is an open top aquarium, so I can see into it again. And they also told me that it has a square bottom, so the bottom dimensions are the same. It doesn't say it's a cube, so I'm assuming that I have a different height. So X, X, and Y are what I'm going to use. We have a requirement that the length times the width times the height has to be 256 cubic feet, so that's X squared, Y is 256. And I want it to be the least amount of glass. So I want the glass to be the least amount. So when I make an aquarium, what I do is I make a bottom. And the amount of glass I'm going to use on that bottom is going to be X squared. It's the area of the base of the glass, right? Then I have a left side. And that amount is XY. And I have a front, also XY. And I have a left, also XY, and I have a back, also XY, and I can make this much more efficiently. I have 4 sides that have all the same dimensions. So this is the glass that's used. Remember, when you're using the glass, it only goes on the outside. That makes it an area dimension. The water goes on the inside. That makes it a volume dimension. And so we're talking about an area or surface area basically here. I run into the same issue that I did before, and that is I have 2 variables in this problem, so I'm going to go ahead and solve for the y, and I'll plug it into my equation. X squared plus 4x times 256 over x squared. I'll clean that up a little bit. I think that's 524. And then it ends up being just over x. Because the x's are going to cancel out. No, that's not 524. It's more like 1,024. I was way off. Whew. Better? Okay. All I did so far was set up my equation that I want to try and minimize the glass that I'm using. I did it with the surface area. I combined like terms. I replaced the y in there that was causing a trouble, and now I'm going to do my derivative, but I run into the same problem that I did in the last problem, and that is I have an x that's in the denominator, and I'm just going to change it to a negative power, and then my derivative will be pretty easy on that. So g prime is 2x minus 1024 over, or times x, sometimes my mind jumps ahead, times x to the negative second. Move that up over here. Which I'm going to set equal to 0. And make it back into a positive power. The solving is very much the same as the solving was on the last problem. I'll bring that 1024 over. I'll multiply the x squared out. I have a cubed answer, not a big deal. I think I can handle it. Divide by the 2. That's 512 equals x cubed. Is that one of our values up there? Did we go as high as 512? Certainly. That is 2, 4, 6, 8. Yep. If it's not, I might have to pull out my calculator. No big deal. So this is 8 is my value of x. And again, I can do a quick check and make sure that this is a minimum. I want the least amount of glass, so I want to make sure that this does come out to be a minimum. And so I'll plug it in this guy up here. If I do 1, I get 2 minus some big number that's a negative. That means it's decreasing. If I do something like 10, I get 20 minus 10.24 or 1.24, 10.24. Anyways, it's going to be a positive value. And so I'm increasing, and so 8 did actually come out to be the minimum that I wanted it to be. And I need to know the dimensions. The thing here is, this is a 3-dimensional shape, so I have 3 dimensions. It's not like the pig pen, which it was length and width. This is a 3-dimensional shape. I need a length, a width, and a height. And so x is 8, and y is 256 divided by 8 squared. 4, great. So this is an 8 foot by 8 foot by 4 foot aquarium. And that's all she wrote on this. That's the last problem I'm doing today.